Okay, good afternoon and good evening, everyone. Welcome to today's multi-body dynamics webinar titled Conduct Vehicle Safety Analysis Using Adams Car. My name is Yijun Fan and I'm the Product Marketing Manager for Adams and EV5. Tim Palmer will be the presenter for today's webinar. Tim is our Field Technical Operations Manager and he has many years of expertise in both CAE industry and also the automotive industry. So after Tim's presentation today, I'm going to conduct a demonstration to basically show you how to perform the ABS system controller validation using Adams MATLAB co-simulation. And following that, we have a 10 minutes Q&A session. So if you have any questions for the presentation or for Adams in general, please type the question down in the Q&A window. We will try to have them answered either during the Q&A session or following the event. Okay, at this point I'm going to pass the presenter to Tim.
Thanks, Yijun. Again, thanks for having me present today. I really appreciate the opportunity to speak to so many of you and talk about vehicle safety analysis. And as Yijun mentioned, I've got a long career in automotive simulation and a lot of that in the vehicle safety area, both in the vehicle dynamics area, but also in vehicle structural analysis and the safety simulation there. So today's webinar, the agenda for today's webinar is we're going to talk just really briefly about vehicle safety, a background, and some terminology for vehicle safety simulations. And then we'll talk about active safety simulation and active safety simulations with Adams Car and a few case studies that some of our customers have used Adams Car to address safety simulation situations. And then we'll talk briefly about passive safety and the type of simulations that Adams Car can support for passive safety simulations. And as Yijun mentioned, we'll do a demo of an ABS system evaluation and highlighting some capabilities to do co-simulations with Adams Car. And then we'll follow that up with like you mentioned, the question and answer. Briefly on safety simulations, we can, when you talk about automotive safety, you can talk about in basically two different areas. One is passive safety and the other one's active safety. And when you think about what these two safety areas mean, passive safety are typically those events where you think about a car crash simulation where you've got an impactor or some vehicle impacting a wall and the occupants protecting the occupants inside there. And in general, these are the features that are designed into the structure of the car to absorb the energy. And when we talk about it, we think about the question that you're trying to answer from that is how best can I manage the energy that's due to this interaction, whether that's with an impact with a wall or a barrier. We want to design into the structure some deformation or energy absorbing features into that and manage the energy of that crash event. So that's passive safety. Active safety, on the other hand, is where we try to sense or anticipate some sort of situation that could be dangerous to the occupants. And then apply some countermeasures. So use this sensor input to decide what we could do to avoid an impact or a collision or some sort of dangerous situation. You can see this in a lot of today's vehicles where we have emergency braking or collision avoidance systems. And other types of features that you see vehicles this is kind of used in lane keeping or crash avoidance or emergency braking situations, and of course ABS systems, which we've had in vehicles for a long time. So trying to use sensor inputs to help us avoid an accident or mitigate the accident effects. So I'm going to go into a little bit more in detail in each of these areas. So in active safety, the business challenges that we see here are that there are pretty complex systems in the vehicle that rely on a lot of sensor inputs, and trying to decide what type of action, corrective action to take with this vehicle, whether it's a steering input or a braking input, to avoid this accident. That's the business challenge. How do we efficiently do that? And if you look at it, the ultimate example of what that might be would be like an autonomous vehicle or a self-driving vehicle. If you think of all the sensor inputs that are needed, and then how does the vehicle decide how to behave in that situation? So whether it needs to, avoid an impact or even just turn the vehicle safely, we need to be able to have some way to predict the behavior of the vehicle in those conditions. So the technical objectives, that engineers are interested in are how do we optimize the control strategies for these types of vehicle situations, these scenarios, and then how do we leverage the investments that we've made into either control system modeling or multi-body dynamics modeling for vehicle dynamics aspects of this, or the structural analysis modeling where we're looking at the stiffness or the NVH, even the NVH type behavior of a vehicle in these types of situations. And really, when we look at this, active safety demands that we really use multi-level modeling. And because, again, like I said, we're using sensor inputs and actuators to monitor and take some action, we have to aggregate an enormous amount of data into this vehicle model, and that can be challenging in itself. And if you look at it, there are different types of tools being used, whether that's to model the control systems or the vehicle dynamics characteristics of the vehicle or the structures. These are all created in different types of tools, and there's different expertise levels of engineers involved. If you're a control system engineer, you don't necessarily have the knowledge of the structure behavior, and how could I include that behavior into the control system behaviors as well. But in general, what we see is people want to use the simplest way that they can model a vehicle. Especially if you're a control system engineer, you want to have a vehicle system behavior, but you don't really have a lot of that knowledge on how that model is created. And unfortunately, by doing that, you can miss a lot of important dynamic performance characteristics that the vehicle may have. So these may interact with your control system model. Of course, you'd like to, make sure that it's rather robust with respect to those, but you need to understand how those dynamic behaviors of the vehicle will affect the control system, and vice versa. So the best strategy is to use multi-fidelity models, what we call 1D or control system type models, along with these 3D models that allow the algorithms and structures to interact and allow us to understand the performance envelopes that we have. And again, those are supported through Adam's car and the functional mock-up interface in Adam's car. I'd like to provide you with a couple case studies on how people can use these approaches to study active safety. And this is from Continental in Germany. And the challenge here was to develop an active suspension system for the Audi Allroad. And their approach was to use Adam's car to build the vehicle system model, the vehicle dynamics model, and then link that with electromechanical models that were created in MATLAB Simulink. And linking these two types of models together in a co-simulation environment, they were able to understand the behavior of the vehicle and model the stability control system effectively. This is then a platform where they can, virtual prototyping platform that they can use to evaluate different road scenarios, different road conditions, and various vehicle parameters, the effect of various vehicle parameters on the stability control system. The second case study is from one of our partners, Red Cedar Technology. They developed the optimization software HEEDS. Now, the challenge here is to optimize a vehicle performance during a high-speed split-view braking maneuver. That's where we have different friction coefficients on each side of the vehicle. And through this, they'd like to minimize the lateral displacement through the braking event and achieve this by varying parameters in both the control system and the suspension. So as you can see it here, there's a little schematic of how they're organized. They use Adams card to build the vehicle dynamics model, and then EZ5 as sensor inputs to a Simulink model that modeled the ABS system. And through this, they ran 50 different evaluations and were able to optimize the performance of both the vehicle suspension and the ABS controller, and reduce the yaw rate and lateral acceleration by 70%. So this example highlights the use of not only Adams car, but the EZ5 and MATLAB Simulink in a co-simulation environment that's driven by an optimization software. Another case is from one of our customers, Meritor, and they're responding to some changes, recent changes in some FMVSS standards. FMVSS stands for Federal Motor Vehicle Safety Standard, and these are the standards that the U.S. government creates that affect many different areas in vehicle safety. One of those is braking performance. FMVSS 105 is regards to hydraulic braking systems, and 121 is regarding to air braking systems. And they specify the stopping distance in emergency braking conditions for heavy trucks and trailers that are equipped with these types of brakes. The changes in that requirement were a 30% reduction in the stopping distances for heavy truck braking. And so the challenges around this is that there's a couple different ways to solve this problem. One is to develop a larger braking system and implement that, which would have some mass penalty and cost penalty. Or they could address this by trying to develop new algorithms that they could implement through their ABS controller. So they were able to use Adams car to develop these models and evaluate various braking strategies and come up with an innovative braking strategy that allowed them to actually exceed the target stopping distance by 28% and using their current disc braking system. So they were able to do a co-simulation with Adams and MATLAB for their braking controller and achieve that target without any sort of mass or cost penalty. Next case study is from Mando. Mando is a large Tier 1 supplier based in Korea, and their challenge was to model an active height control system for their vehicles, so or that they provide for vehicles. And so this type of system reacts to different payloads and keeps the height of the ride height of the vehicle consistent. And so it has to operate in different load conditions and vehicle handling events. So the Mando implemented this control system modeling along with an Adams vehicle model to model the various dampers and ride springs so that they could understand the vehicle behavior under extreme handling events for these types of vehicles. I'll move on to passive safety here, and I think passive safety, as I mentioned before, is more of the structural design of the vehicle, but there's aspects of these types of events that lend themselves very handily to Adams car simulations. And when we look at the trends in the auto industry where we're trying to reduce the weight or reduce cost, these can affect some of the structural performance of the vehicle. We also want to reduce the physical tests significantly in this area because these tests are very expensive and very time-consuming And actually testing can give us a lot of data, but it can't give us some special data that we can actually get from these passive safety simulations. In Adam's car, we've implemented some roll stability events that are targeted for rollover simulations, and these help provide the boundary conditions for subsequent structural analysis or identify conditions where the vehicle may roll over. Rollover is a very critical event in vehicle safety simulation. There's really only about 5% of all traffic accidents are rollovers, but that 5% accounts for 30% of the fatalities in crashes in the U.S. So it's very important for us to be able to understand the vehicle dynamics or the attitude of the vehicle or the roll rate of the vehicle as it's going into a rollover event. Some cases we might find, like in this situation, that the vehicle actually doesn't roll over, which is good for us to know what conditions the vehicle would roll over in, and what areas maybe we'd have to deploy some countermeasures like airbag deployments. So this is a very good information for safety system designers and developers to have when they want to create a vehicle safety system that addresses rollover. So these roll stability events, we have 3 different events. We have a sand bed, which is quite analogous to the ECE R66 that's used for bus rollovers, where there's a plate that's lifted up until the vehicle slides off this plate and onto a surface. In this case, we can model different stiffnesses of that surface as well. So it could be a soft soil, rigid surface that vehicle rolls onto. The second one is an embankment, or what we call somebody call a high ditch event. And this embankment, a vehicle can roll over down an embankment. There's a small ramp that it would induce the rollover event as well. In this case, we can model it as a rigid road type, or have a soft soil or a loose sand modeled in this as well. And there can be some steering input added to this event. And then the third one is a corkscrew ramp. This is a ramp that's on one side of the vehicle, and the corkscrew ramp geometry can be modified to match the tests that you're actually conducting. And again, the vehicle may or may not roll over. I think this is another one of those events that's somewhat critical to understand what is actually happening to the vehicle. As the vehicle goes up over this ramp, there's one point in time when the entire weight of the vehicle is up on one corner of it. So there may be some need to model the nonlinear behavior of the vehicle structure locally as well, to understand what's actually happening with the suspension geometry, and will it actually roll over. So this is another area where Adam's car can provide a great deal of value in these simulations. So now I'll turn it back over to Eugen, and we'll talk about a co-simulation with Adams for an ABS system.
Okay, thank you, Tim. So after the introduction of so many different vehicle safety analysis that can be performed with Adams, now let's go through a demonstration. Hopefully we can get a deeper understanding of how Adams car can be used in those type of analysis. Okay, first we will let's open an assembly model in Adams car environment. So basically, we will be opening a vehicle model with a front-wheel drive system in the vehicle. And what we do here in Adam's car environment is to prepare for the files that's needed to perform the downstream code simulation between Adam's car and the MATLAB Simulink. Okay, now the vehicle is loaded. We can take a look at the interface now. Before we go ahead and perform the vehicle event, we want to make sure that we go to the plugin manager and load the Adams controls plugin. So make sure that's loaded before you perform prepare anything for the code simulation. And now what we want to do is to basically conduct a straight line event with the braking on the split mill scenario. So we go to the straight line events and then brake. So in this interface, we will input some values for the code simulation events that we are going to conduct in the later steps. So here we can define the output prefix as the ABS. So we will have 4 seconds of simulation with the 400 steps. We specify the simulation mode as files only, since we are not really calculating anything at this point. We're just preparing for the files that's needed for the code simulation. And the road types, we will pick a smooth road with a split mill scenario, and we will log the steer. The initial velocity is 70 kilometers per hour. The final brake, let's set it at 100, and the duration of step is 1.5. Check, and we will. So before we perform that vehicle event, so this is the working directory for both Adam's car and the MATLAB. So here you can see the only 2 files here are the controller algorithm that will be loaded in the MATLAB environment. So those are the only 2 files that's available currently in the working directory. And now we are gonna start time. Let's specify 1. So after this calculation, if we go to the working directory, you can see all those new files that's created with the new events performed. Next, what we want to do is to go to controls and plan export. So now we want to set up the connection between Adam's car and the Simulink. And in this case, we will define the file prefix as ABS brake, and choose and select the input signals. So the input signals means the input from MATLAB into Adam's car, which is basically the signals that asks the brake system to either release the brake or continue braking. And we will also define the output signal, which is basically the wheels, the speed of each of the 4 wheels. So how this code simulation works is that Adams will calculate the wheel speed based on the specific road type and the vehicle parameters, and it will export the speed of the 4 wheels into MATLAB, and depending on the slip ratio, which is the which is basically the difference between the vehicle speed and the specific wheel speed divided by the vehicle speed, and that is what we call the slip ratio. So the larger the difference is between the wheel and the vehicle, the more slip which basically will occur. And the more slip if the slip ratio is larger than what we call the ABS threshold, the brake will be released. So in order to avoid slip. If the value is smaller than the ABS threshold, we will continue to brake the vehicle, the wheel. And here the target software, we will choose MATLAB. Of course, you can also choose any other software that supports the FMI standard here to run the code simulation. With this setup, we will click OK. So what this step does is to update the M file, which is basically the connection file between Adams and MATLAB. So to this point, we're almost done with the operations in Adams car environment. Now we can go to the MATLAB interface. There are a few files we need to load into the MATLAB to perform this code simulation. The first file is what we call the ABS brake. So this is the file that we defined earlier, which basically describes the inputs and outputs from between Adams and MATLAB. The second file we want to load is the ABS setup, which is basically the ABS controller in MATLAB environment. So we will drag this into the MATLAB window, and this will take about 1 minute to load. And after that, we will basically run the Adams system file, which is the Adams, which is basically the Adams subsystem representation in the Simulink. So here you can see this is this is a simplified version of the real ABS controller, because in this specific controller you will see some of the basic logics, but we didn't capture some of the higher fidelity issues like the hydraulics in the brake systems. But you can certainly do that using Simulink or other control softwares. Okay, so this is the controller we defined, and then we are going to load the Adams system model in MATLAB. Okay. Next step is to replace this Adams block in the controller with the updated Adams subsystem file. Okay. Now the code simulation is all set up and it's ready for us to run the simulation. The simulation will take about 3 to 4 minutes to finish, and of course it depends on the fidelity of your vehicle model and also your MATLAB controller, how sophisticated or complex your controller is. To save some time, we have already got the results from this particular code simulation. Besides, we have also performed a basic Adams vehicle event without the ABS controller. So now we have 2 vehicle events in parallel for comparison. The one you see in the upper left corner is the vehicle event, the split mu vehicle event with ABS controller. And the lower one you see here is basically the same vehicle, but it's the split mu event without the controller. And we can run the simulation, and you will see the difference in a few seconds. So you see with the ABS controller, the vehicle is braking pretty steadily, but the one without the ABS controller, the vehicle is slips to the side of the road. Let's see that again. And also, let's take a look at some of the results. So there's one parameter that we want to just focus right now. Is what we call the longitudinal slip front. So as you can see from the curve, the red curve stands for the results without the with no ABS controller, and the blue curve stands for the one with the ABS controller. And for the red curve, you can observe there's a constant slip in the vehicle since the vehicle starts to brake. It's about minus 100. For the event with ABS controller, we can see that the slip between the tire and the ground is minimized to a certain amount, and that can be used to verify how effective your controller is in the MATLAB. So that's pretty much it for the demonstration. So what we really can get from this code simulation is that we can not only capture the you can not only specify the complex control algorithms in MATLAB, but you can also capture the real physics behind the vehicle, behind your vehicle model. So it's and also both Adams and MATLAB, both solvers are contributing to the code simulation with their own specialties. So Adams solver, it calculates the vehicle dynamics side of the simulation, and MATLAB solver calculates the controlling side of the simulation. So we're leveraging the advantage of both software, and both software is contributing to the real physics behind this ABS controller scenario. So that is what we want to cover in the demonstration. So now I'm going to turn the slides back to Tim.
Yeah. So to summarize, the main points we wanted to cover today were that Adams car can address many of the challenges that face engineers who are responsible for safety simulations. So that's in both the active and passive safety regimes. And linking Adams with 1D simulations for controllers provides a really unique tool to study advanced vehicle dynamics and safety simulations. And that's primarily through this functional mock-up interface, FMI capability that Adams has, that's been available since the 2013 version of Adams. And leading companies are using this strategy to innovate and making the most of their current development tools. And we look at these things. We want to try to reduce testing. We want to expand the set of variables that we could consider in these studies. We want to look at different new scenarios that maybe we need to investigate. And these help us provide more innovative solutions, is to come up with different strategies or unique capabilities that these vehicles can address. And some of the newest features of Adams, such as the roll stability events, address some of the most challenging safety problems that we see, and that's when a vehicle dynamic event turns into a rollover event. And those are features that are available in the recently released version 2014 of Adams. And MSC can not only provide the software, but also the services to help you get through these tough sorts of problems. Help bring up your capabilities with simulation capabilities, or provide resources that you can use to perform these types of simulations. And with that, I'd just like to thank you very much for attending. And I'd really like you also to, if there are some questions, we'll try to answer those and make sure you put those into the Q&A section here. And we'll do our best to answer those with the time we have available. And then we'll also, if we can't get to all the questions, we'll try to answer you by email, or and I think we also we have our contact information here on the screen, so feel free to contact us